Hello everyone. Today I am going to explain about recurrence relations. Now, what is the definition of recurrence relation? How to solve this recurrence relation? Today I will explain. Recurrence relation. A recurrence relation that allows us to run on and on through the terms of sequence. If you get the terms on and on, then we say that it is a recurrence relation. To solve the recurrence relation, there are various methods are there. The first method I am using is method of solving recurrence relation by complementary function and particular integral method. Now in first year M2, in first order first degree differential equations, we used to solve the equation complementary function CF plus PI method, complementary function and particular integral method. That method I am using. Method of solving recurrence relation using CF, complementary function, and particular integral method. CF by L, using LHS we will get CF, by using RHS we will get particular integral. Using that method I am using. Now, if the given equation, given recurrence relation is in the form of A, un plus 2 plus B, un plus 1 plus C, un is equal to f of n. This is LHS, this is RHS. Based on the RHS, we will get particular integral. Based on the LHS, we will get complementary function. The degree from higher order to lower degree, you will get. Remember, using the LHS, you will get particular. Using the LHS, you will get complementary function. Using the RHS, we will get a particular integral. Now, given that initial conditions u0 is equal to alpha, u1 is equal to beta, we proceed as follows. The formulas part I will tell you, and then we will do the problems. Now, step 1. First of all, by using the complementary function particular integral method, we have to find the complementary function using the LHS. Finding the complementary function CF. Depending on the nature of the roots, by using the LHS part, we have to write the auxiliary equation. Auxiliary equation, find the roots of the auxiliary equation. Depends on the nature of the roots, we will get the complementary function. If the roots are real and distinct, if the roots are real and distinct, lambda and mu, two roots we have got, then the complementary function will become C1 lambda to the power of n plus C2 mu to the power of n. Now, if the roots are real and repeated, lambda, if the roots are repeated, you will get a C1 plus C2n into lambda to the power of n. Now, if the roots are repeated, you will get the formula like this, C1 plus C2n into lambda to the power of n. If the roots are conjugate complex numbers, or e to the power of plus or minus I theta form, then the complementary function will become r to the power of n into C1 cos n theta plus C2 sin n theta. Like that, you will get the complementary function. Depends on the roots, you will get the complementary function. And then step 2, finding the particular integral. For this also we have few formulas. Finding the PI, particular integral, finding the particular integral by the method of indeterminate coefficients. Now, what is this method and how to? If the RHS type of the term means, if the RHS is in the form of, in the given recurrence relation, if the RHS is in this form, a to the power of n, for suppose there is one RHS is in the form of 2 to the power of n, or 5 to the power of n, or 3 to the power of n, something like that. If the RHS type of the term, if the RHS is in the form of a to the power of n, then the trial function or the particular integral, this is the particular integral, this is the PI, particular trial function means particular integral. The particular integral will become a into a to the power of n, capital A into a to the power of n. If it is in the form of just a to the power of n, if it is in the form of the RHS is in the form of a to the power of n, and a to the power of n, the particular integral is a to the power of n. When will we get this one a to the power of n? If an is in CF contains a to the power of n. If CF contains a to the power of n, this will become the particular integral of this. Now, only simply a to the power of n is in the RHS. This will become the particular integral. Now, if this is the RHS, a to the power of n is in the RHS, as well as CF contains a to the power of n. This will become a to the power of n is the a to the power of n is the particular integral. Now a to the power of n is the RHS as well as CF, complementary function, contains an and n a to the power of an a to the power of n and n a to the power of an are in CF, then this will become the particular integral. If these two terms contains in CF, then this will become the particular integral. If a to the power of n is in CF, then this will become the particular integral. This is about the first one. And second one, if RHS is in the form of a to the power of n into alpha n square plus beta n plus c, if a to the power of n into something like that alpha n square plus beta n plus c, then our particular integral will become a to the power of n into a n square plus bn plus c. If I take higher order polynomial if needed, if it is a necessity, we can take a higher order polynomial also. Means alpha n cube plus beta n square plus something like that. Higher order polynomial if needed, we can take. Now a to the power of n into, if RHS is in the form of a to the power of n into alpha n square plus beta n plus c, this will become the particular integral. Now if RHS is in the form of simply alpha n square plus beta n plus c, then a n square plus bn plus c will become the particular integral of this one. Now take the higher order integral if needed. Now if RHS is in the form of cos alpha cos Na plus beta sin Na, then this is the particular integral. Now a to the power of n into alpha cos Na plus beta sin Na, then this will become the particular integral. This is the about formulas. Using the initial conditions also they will give you C1, C2 we have to evaluate and to get the original solution. If we are using the initial conditions, we have to find the constant C1, C2 and all. Now these are the formulas, AN like this, all the four formulas. Now remember and by heart. Now we will go to the first problem. In the first problem, what is given? Solve an plus 2 minus 3an plus 1 plus 2an is equal to 2 to the power of n. N is greater than or equal to 0. Given, what are the initial conditions? A0 is equal to 3, A1 is equal to 6. A0 is equal to 3, A1 is equal to 6. Initial conditions are given. Now, using this given problem, first we will write the auxiliary equation from higher order to lower order. M square minus 3m plus 2 is equal to 0. M is equal to, if you find the factors of this one, m is equal to 1 comma 2. Therefore, complementary function, distinct roots we have got. Therefore, C1 into 1 to the power of n lambda to the power of n plus C2 into mu to the power of n 2 to the power of n. 1 to the power of n is nothing but 1. C1 plus C2 into 2 to the power of n. This is CF. We have got CF in this form. Because the roots are distinct. Distinct roots formula is there, then that one use the formula. Now we have to choose the particular, assume the particular solution is an is equal to, now observe the RHS. RHS is in the form, in which form? 2 to the power of n is there in the RHS. RHS is in the form of 2 to the power of n. That means RHS is in the form of a to the power of n. A to the power of n. Therefore, as well as CF contains 2 to the power of n. See here, if RHS is in the form of a to the power of n, then this is the answer. If RHS is in the form of this one, as well as a to the power of n is in a to the power of CF contains a to the power of n, then what will particular integral be? A to the power of n. Now our CF contains 2 to the power of n. Our RHS is in the form of 2 to the power of n. Our CF contains 2 to the power of n. Therefore, our particular integral will become an 2 to the power of n. Now, in our given problem, n plus an plus 2, an plus 1, an. 3 terms are there. This is an, means an plus 1 is equal to, wherever n is there, in place of n, you put n plus 1, 2 to the power of n plus 1. That is equal to an plus a into 2 to the power of n plus 1. Next, an plus 2. an plus 2. a into, wherever n is there, substitute n plus 2 into 2 to the power of n plus 2. That is equal to an plus 2a into 2 to the power of n plus 2. 2 to the power of n plus 1 we can write as 2 to the power of n into 2. 2 to the power of n plus 1, 2 into an plus a whole to the power of 2 to the power of n. Now 2 to the power of n plus 2 we can write as 4 into an plus 2a whole to the power of n. Now what is our given problem? Our given problem is, now I will write our given problem, an plus 2 minus 3 an plus 1 plus 2 an is equal to 2 to the power of n. I will write that one. An plus 2 minus 3 an plus 1 plus 2 an is equal to 2 to the power of n. Now an plus 2 value is how much? 4an. From this I am writing 4an plus 2 4s are 8. 8a into 2 to the power of n minus 3 into an plus 1 is how much? 2an plus 2a into 2 to the power of n plus 2an. an is how much? an 2 to the power of n is equal to 2 to the power of n. RHS is 2 to the power of n. Now 2 to the power of n, 2 to the power of n get cancelled on both sides. The remaining I will write. We can cancel both sides. 2 to the power of n contains all terms. That when we can cancel. 4an plus 8a minus 3 2s are 6an plus minus 3 2s are 6a minus plus 2an is equal to 1. We cancelled both sides. Now comparing coefficient of n on both sides. Comparing coefficient of n on both sides. Observe this one. Comparing both sides, the coefficient of n. 4a minus 6a plus 2a. n terms. 4a minus 6a plus 2a is equal to n is 0. How much you will get? A is equal to 0. In the next step, comparing constant terms. Comparing constant on both sides. If you compare constants, 8a minus 6a is equal to 1. 8a minus 6a is equal to 1. 2a is equal to 1. a is equal to 1 by 2. We have got a is equal to 1 by 2. Therefore, what is our an? How much is our an? Capital A into our an is an 2 to the power of n. an 2 to the power of n. That is equal to a is equal to how much we have got? 1 by 2 into n 2 to the power of n. Now an is equal to CF plus PI. CF is how much? This is an. The complete solution is, this is CF, complete solution CS. The complete solution is equal to CF plus PI. This is only PI. This is only PI. Now I am writing complete solution. CF plus PI. CF is C1 plus C2. How much is CF? C1 plus C2 into 2 to the power of n plus PI is 1 by 2 into n into 2 to the power of n. Now we have to find C1, C2 constant terms, C1, C2 values we need to find. To find C1, C2 values, we will use the initial conditions as well as n greater than or equal to, in the given problem, n greater than or equal to 0 is given. That means either is equal to or above is equal to 0, either is equal to 0 or the n is greater than or equal to 0, and a0 is equal to 3, a1 is equal to 6 also given. Now put n is equal to, because n is equal to greater than or equal to 0 is given, n is equal to 0. If n is equal to 0, wherever n is there in this one, wherever n is there in the above equation, we'll put a0 is equal to c1 plus c2, 2 to the power of 0 into 1 by 2 into 0 into 2 to the power of 0. a0 is equal to c1 plus c2. Now put n is equal to 1. a1 is equal to c1 plus if you substitute 1, how much you will get? 2c1 plus 1. Now equation 2, equation 3. But a0 is given. How much is a0? a0 is equal to 3. 3 is equal to c1 plus c2. a1 is equal to 6. 6 or 5? a1 is equal to 6 is equal to c1 plus 2c1 plus 1. Therefore 6 minus 1 is 5 is equal to c1 plus 2c1. This is 3 actually, this is 2 actually. We substituted a1 and a2 and solving 2 and 3, we get c1 is equal to 1, c2 is equal to 2. Now therefore the CS complete solution is an is equal to c1. This is CF plus PA. C1 plus C2 values we will substitute. a1 is equal to, C1 is how much? C1 is equal to how much? 1 plus C2 is equal to 2. 2 into 2 to the power of n plus 1 by 2 n into 2 to the power of n. This is the answer. CS means complete solution. Thank you very much.